Okay, that should do it. So as I was saying, amplitudeology is some word I made up for the study of amplitudes. So in general, scattering amplitudes could have any number of particles coming in. So there's some kind of plane waves of definite momentum and any number going out. Of course, for applications to things like the Large Hadron Collider, we're usually interested in two particles or two partons coming in and generic numbers going out. And I want to give you a sort of survey of the kinds of methods that people use in this field and some of the results that can be found. But before I go into details, I just want to give some motivation. So what are the different reasons why people are doing these things? And they have a broad range of reasons. By the way, I'm pretty jet lagged today because I flew from California. So if I say something stupid, it's only because I'm jet lagged, not for any other reason. But feel free to correct me, ask questions, interrupt at any time. You might have to yell if I'm facing the blackboard or something. Anyway, as I was saying, one of the reasons, or the first reason, is a sort of practical reason or phenomenological reason, which we might just say as a shorthand QCD at the LHC. That is, we need to have better techniques to calculate theoretically with higher precision, especially for standard model processes at the LHC, in order to know what the standard model predicts so that we can subtract it off and see if there's any new physics left over. Or in order to make measurements of, say, the properties of the Higgs boson, we need to know how many Higgses are we supposed to produce in the standard model and multiply that by the branching ratios and so on. And in general, the thing about scattering amplitudes is they are in theory, they're part of QFT, quantum field theory. They're not just a small fraction of the things you can do in quantum field theory. But in some sense, they're sort of where the QFT meets experiment, okay? Pretty much most experimental measurements are measuring cross-sections that are computed by calculating scattering amplitudes and then squaring them. And so they're sort of where the rubber meets the road for quantum field theory to make contact with experiments, and especially at the LHC these days. To put it in a little more context, in QCD we have an expansion in alpha S, and there are leading order terms which come from calculating tree graphs, next to leading order terms where you need loop graphs, next to leading order terms where you need two loop graphs, and so on. And we can sort of put up a scorecard of where we're at. Basically, there are very efficient programs out now to produce leading order cross sections and even to merge them with Parton shower Monte Carlos to cover events with many, many jets, 7 or 8 jets and other complicated processes with multiple objects in them. So that's sort of under control. But we can also ask, what kind of fractional uncertainties do we get when we calculate cross sections at leading order? Well, it depends on the process, but you can have up to 100% uncertainties in a leading order calculation. It's really very uncertain what the value of the cross section is. So then at NLO, we're also in very good shape. We can now calculate things with 2 goes to 4, 5, in some cases 6 objects in the final state and next to leading order. And a lot of that came out of some of these methods that I'll try to explain in the course of these lectures. And when you go to next deleting order in alpha S, you bring this up to 100% uncertainty down to something that depends on the process, but could be 10% uncertainty in some cases, maybe 30% uncertainty in bad cases. And then when you go on to NNLO, there's been a huge amount of progress made recently for 2 goes to 2 processes, also 2 goes to 1. So 2 goes to 1 and 2 goes to 2 are in pretty good shape by now. But if you ask for 2 goes to 3, we still don't know how to do any objects with any processes with 3 objects in the final state at the LHC. But when you go down to this level, you can get to of order 1, and then maybe in worst cases, I don't know, 8% or something uncertainties, depending on the process again. And then there's n cubed LO, for which we only know one process at present. That's a 2 goes to 1 process, which is glue goes to Higgs. And now that you're getting down to a few percent in theoretical uncertainty. By the way, there's also, when you start getting to higher accuracies over here, you should start worrying about electroweak corrections too. And so there are various processes where a lot of processes have been calculated at next to leading order in electroweak. So that's sort of the state of the art there. This matters in different kinematic. How important this is depends somewhat on the kinematics. Anyway, this is sort of the practical motivation to improve our knowledge of the standard model at the LHC. So another motivation is more formal structure, let's say. There are a lot of beautiful patterns in the structure of scattering amplitudes that we'd like to understand better, and maybe use that better understanding to feed back into the practical. So basically we want to understand how are amplitudes put together, and what's the best way of understanding that. So here's just one invitation, which is if we take at tree level, this closed blob with no holes in it is supposed to be in the sum of all tree Feynman diagrams. And we're going to have all of these particles be gluons. And we're going to take the case where all of the outgoing gluons are plus. We find that amplitude is 0. In fact, even if one of them is minus, those amplitudes vanish. And if we then redo it with gluons and make 2 of them, so we have a bunch of plus gluons, and then we have two negative gluons. Then this amplitude, we'll explain the notation later, but the remarkable thing is that it can be written down as a one-term expression with a number of factors which I'll explain as we go along, but it just evaluates to a simple analytic expression with just one term. And this is called the Park-Taylor amplitude, and it's about 30 years old. And so sort of this is just an invitation to understand the structure of what's going on with these kinds of amplitudes, and similar sort of miraculous simplicity that you see at the loop level as well. So this formal structure, this is an example of something where if you look at the Yang-Mills Lagrangian, it's basically impossible to see this structure directly. And so these are relations, we're talking about relations that are invisible at level of Lagrangian. So people working in this field, they use Lagrangians rather sparingly and try to develop other techniques as well. In fact, some of the techniques are called on-shell because they take a lot of advantage of the fact that all these particles here, the external states, are on their mass shell. In fact, now we'll see if I can did this topologically correctly. We have a slogan. It's topologically correct, but still not good enough. We have a slogan, on shell good. Of course, that comes along with another slogan on the back, which is off shell bad. So the philosophy is that you should always try to make as many things on shell as possible. And technically, these things are called on shell diagrams, but there's also sort of an on shell philosophy, which is related but somewhat independent from on shell diagrams. So anyway, now that we got that out of the way, more generally, there are a lot more issues that come up with this formal structure category. This was the slogan at a TASI that I helped organize a few years ago. And the students liked it, so they put it on a t-shirt. So another thing that sort of goes under this same general heading is that amplitudes in different theories are related in ways that are not at all obvious from the respective Lagrangians. So the sort of first example of this is something that is called gravity is Yang-Mills squared. So roughly speaking, amplitudes in this theory look like the square of amplitudes in this theory. But there are other kinds of relations that generalize this or discuss other kinds of theories where you sort of take products of two theories and construct another amplitudes in another theory out of that. And so a lot of the early methods in this area were actually this on-shell approach involves techniques that actually date back to the 60s. So S-matrix analyticity, and that includes things about how amplitudes factorize in various channels, unitarity. So these are from the 1960s, but then to combine them with the scaffold of perturbation theory. In other words, make use of very general principles, but also understand how they combine with perturbation theory, which has a lot of structure to it. And so these make, well, there's also in here is causality. This is closely related. But then another question is, can we formulate things without using locality and causality. But do it more geometrically. And that has been a theme that has led to something called the amplituhedron. Now, I'm not going to really go into the amplituhedron in these lectures, but maybe it'll be a starting point for people who are interested in that to go off and explore further. So, but the point is there's a lot of understanding of the role of analyticity. You can even use analyticity to, in some sense, construct the amplitudes and build them up. But then it led to the question, this is by Nima Arkani Hamed and Yaroslav Trinka, whether there were other formulations in which the causality was not the input, but was an output of a more geometrical picture. So then there's also sort of other kinds of spin-offs and connections. So besides the practical applications to QCD at the LHC, you can also apply these methods to more formal theories where you can get to very high loop order. So maybe I should say other applications. As Csaba mentioned in his lectures, we don't have a great understanding of quantum gravity. However, we know that when we make quantum gravity supersymmetric, the divergences in the theory are delayed quite a bit. So, for example, for the maximal supergravity n equals 8, we know that it's actually UV finite now through at least 4 loops, probably 5 loops by now. And some of that is we've learned through explicitly building the scattering amplitudes for this theory to high loop orders. Another interesting application is to amplitudes in planar n equals 4 super Yang-Mills. So this theory is the prototype for the ADS-CFT correspondence. And planar means that you take the gauge group to be SUNC, and then you take the limit NC goes to infinity. And in this limit, you get a bunch of extra symmetries and cool things happening. There's an integrability. Quantum integrability allows you to solve certain things exactly in the 't Hooft coupling. The 't Hooft coupling is the product of G Yang-Mills squared for this theory times NC, and you hold that fixed. When you take this limit. So there's an extra set of symmetry generators, an infinite dimensional symmetry that happens that lets you think that this theory can be exactly solvable, and in some cases you can in fact do that. And there's also connections to mathematics. So some of it is to, for example, to combinatorics these on-shell graphs are cubic, and they have two different colors at the vertices, white and black, although it's not exactly black here. But anyway, those are called bipartite graphs when they have two colors. So there's a close relation between these graphs and working out the combinatorics of these bipartite graphs, and also geometry in the sense of and then there's also other mathematics that's associated with the kinds of integrals that you get for multi-loop. You get things called iterated integrals, and they're also closely related to other things that mathematicians have been studying a lot recently, like multiple zeta values. So the zeta n is the sum, and it has generalizations with multiple indices on it. And there's a lot of interest in the types of these zeta values, but they're embedded in a larger structure of functions called iterated integrals. So there's a lot of mathematical connections too, and maybe one last motivation would be to look for other kinds of applications that are not strictly about scattering amplitudes. And one example would be to try to use gravity equals Yang-Mills squared somehow to do things like compute LIGO binary in-spiral waveforms. So this isn't something that's really happened in practice yet, but people are thinking about it. In other words, you can compute these in-spirals in Newtonian gravity, but you have to take into account higher order corrections. I think Ira mentioned something about the fact that there's an EFT expansion, and roughly speaking, as two compact objects get close to each other before they merge, you get corrections to the Newtonian approximation that become more and more important, and they involve, very roughly speaking, things that look like gravitational amplitudes, although with these black hole sources here. And because of the nonlinearity, you get things that involve a number of the gravitational vertices. And maybe you can simplify that by using some of these relations. But that's still more for the future. So I gave a rough list of topics that I was planning to cover in the which is on the web page. I'll just briefly write them down here too, and then I'm going to put one more in, squeeze one more in, because after all I've got about 9 hours or so. That's a lot to fill up, and so before we sort of go on to really talk about amplitudes, I want to just do a little back of the envelope LHC physics. And then we'll go on to talk about color kinematics basics. And then I'll talk about trees, and we'll talk about modern on-shell recursion relations, BCFW recursion. And then we'll talk about unitarity for loops. And some simple loop integrals, and then I'll discuss iterated integrals and some of the techniques that people use to discuss them, such as something called the symbol. And then we'll do an application which is to look at bootstrapping six-point amplitudes in planar n equals 4 super Yang-Mills. So that's roughly the layout. And there are lots of things going on in amplitudes that I won't have time to cover. Anyway, any questions before I sort of do a little back of the envelope LHC physics, just to give you guys an introduction to that? So the LHC is a remarkable machine, and phenomenologists are lucky to be living in the time when it started operating. You might think it hasn't discovered anything but the Higgs, and basically that's true, but it's still very early in terms of the amount of data that it's going to collect over the long haul. And so it's a machine that has, if you want to put it on a map, here's sort of Lake Geneva. And this is sort of the tip of Switzerland. And this is France over here. And somewhere over here is CERN. And here is Atlas, somewhere where the LHC meets. That's one of the two large high PT detectors. And the other one is kind of over on the other side of the ring. And this circumference is 27 kilometers. So so there's a map. Now we're going to like zoom into one of these regions and blow things up by about a factor of 10 to the 9th. And when you go by a factor of 10 to the 9th, you're way inside the detector now, and you have what you can see is two bunches of protons coming at each other rapidly. So we have 10 to the 11th protons in one bunch, 10 to the 11th in the other bunch. And these bunches are only about 15 microns transversely. They're a lot longer. They're like 30 centimeters long. So kind of macroscopic like that, these very thin ribbons coming at each other. And each proton carries, so the center of mass energy nowadays is 13 teravolts. It'll probably be that for a long time. So that's 6.5 tera electron volts per particle. And that's almost a macroscopic amount of energy just per particle. So if we take this 6.5 times 10 to the 12th and we multiply by 1. So that's EV. And then the number of joules is 1.6 times 10 to the minus 19. So that's about a microjoule. But they're 10 to the 11th particles. So this bunch alone has 10 to the 5th joules in it. And there are 2,808 bunches in the ring. So the amount of energy stored in each beam is about 300 megajoules. So that's a lot of energy. That's macroscopic. In fact, this is the kinetic energy of an aircraft carrier if it's going at about 5 or 10 knots. or maybe more relevant, it can it's enough energy to melt 1 metric ton of copper. So basically, if you go around this ring, there's exactly one place you can lose the beam and not destroy that part of the machine. There's an abort line that you can take these 3,000 bunches out through, and it has some kind of equivalent of a ton of copper to absorb that kind of load, which is why they were very careful when they were tuning up the machine. But now it's been running great. There are large numbers of collisions, and we want to how do we characterize the performance of an accelerator in a convenient way so that we don't really have to know everything about the machine? And the way we characterize it is in terms of the integrated luminosity. And at any given time, the machine has a specific or instantaneous luminosity. But basically what you care about when you examine a certain data set is how much of this integrated luminosity was collected, and it's a shorthand for how many numbers of events that you expect to get. So if you have a process that goes to some state I, then the number of events is the cross-section, which is measured in square centimeters, or usually barns or femtobarns, times this integrated luminosity. And since this is a number and this is an area, this is the inverse of an area. So it's usually quoted in some weird unit called inverse femtobarns. Let me write down what so a barn is defined to be 10 to the minus 24 square centimeters, and femto 10 to the minus 15. And just to give you some numbers, in 2016, the LHC collected, well, roughly 35 inverse femtobarns, and then last year collected about 50 more. So give or take about 100 inverse femtobarns at 13 TeV. A little less, but they've also collected some at lower energies too. And so now let's give an example just to run the numbers. By the way, so we'll come back to this in a little bit in a little more detail, but here's a rough picture of what a short distance event at the LHC looks like. You have, so this is now blowing up this picture by another factor of 10 to the minus 8 or something. And these protons here, roughly speaking, have a radius of order 1 femtometer, or 10 to the minus 13 centimeters. So if they were black disks, their area would be on the order of 10 10 to the minus 26 square centimeters, which would be 1/100th of a barn, or 10 millibarns. Now, the actual total cross-section for 2 protons at LHC energies is a little bigger than this. It's like 100 millibarns. So every time you put 2 protons in a bunch, you have a very large, relatively large probability of getting a collision. And in fact, these bunches are so intense that from this size cross-section, you don't just get, you get about 15 to 40 events every crossing when the LHC is running at top luminosity. Now, most of the time, all of those events are boring events. That is, they're very soft and don't produce, they're not exploring very short distances within the proton. But an example of a short distance process would be if a quark out of one proton finds an antiquark and annihilates into a Z0, a Z boson. And then this could then materialize, say, into an electron-positron pair. And then the spectators, the other quarks and gluons inside the proton, will basically go down the beam pipe. Maybe they'll be disrupted a little bit, and you'll get other stuff going on. Plus, you will have 15 to 40 other events in which most likely nothing interesting happened. So the cross-section for this, which is the kinds of things that you can compute eventually to higher order using these techniques, is 50 nanobarns. So that's, a million times smaller than the total cross-section, but it's still a big number. It's 5 times 10 to the 7th femtobarns, because nano is 10 to the minus 9 and femto is 10 to the minus 15. And so this is at 13 TeV. So if you take, this number and multiply by this, let's just call it 100 inverse femtobarns, you get roughly 5 billion Z bosons at the LHC. So that's an awful lot of Z's. Now, most of these didn't have a chance of being seen by the detectors because the Z decays most of the time into quark pairs, and it only goes to E plus E minus a small fraction, 3%, and a similar fraction to mu's. And then there are also taus, which are actually hard to see. So only 6% of the time do you get an easily identifiable Z, and some of the time you'll miss the electrons and the muons, but still you get millions of Z's. So this is an example of a process that's sort of called a standard candle. We know from studies at LEP and elsewhere in the 90s, we know the properties of the Z very precisely. And so with millions of them, you can use this to understand your detectors even, and also measure the structure of the proton or constrain it some. So let's just do the numbers on one other particle, the Higgs boson. So why can't you see the Z when it goes into quark and antiquark? Any ideas? Yep. That's right, because the Z is produced electromagnetically, so, well, electroweak. So this coupling G here has the property that its coupling strength is G squared over 4 pi, which is alpha weak, which is about 1 over 40. But you could also replace this process with annihilation of QQ bar into QQ bar through a gluon. Or it could go to 2 gluons. Anyway, there are a lot of ways to produce jets. In fact, a lot of them involve gluons, which have a much larger probability, as we'll see in a second. And so this thing here, is probably down by 10 to the 4th to 10 to the, I forget exactly, compared to the jet cross section, it's very small. Now there are ways to try to enhance the signal in some cases. Some of the time this is a B quark, and B jets are a little rarer. And then you can try to use jet substructure techniques, but that's still a very difficult thing to do. Okay, now we're going on to the Higgs boson. So after a lot of work, the cross-section for computing the Higgs boson at 13 TeV, cross-section for producing the Higgs boson at 13 TeV is on the order of 60 picobarns. So that's about 1,000th of the Z cross-section. And so it might amaze you to learn that the LHC made already about very roughly 6 million Higgses. As in the case of the Z, most of those Higgses are completely undetectable. The main decay of the Higgs is to BB bar, and it's impossible to see it unless you know something about X, about other things that are associated. So the Higgs has now been seen in a number of modes, but the modes that are actually the cleanest are gamma gamma, and that happens only 0.2% of the time. And also you can go to 2 Z's, although one of them has to be off shell, and these Z's can decay to leptons, and generally L stands for either E or mu, the 2 leptons that are easy to distinguish from other particles at the LHC. And this happens at about 10 to the minus 4. So if we look at the case of gamma gamma, we can take this 0.2% times 6 million Higgses, and we get roughly 10,000 photons. But you don't get to see all of these because some of them are outside the acceptance of the detector or at too low a transverse momentum to be picked up. And so maybe you get 2,000 gamma gamma events. But the background, which is more or less QQ bar to gamma gamma, is a factor of 10 or so or more bigger. And so what you see is you plot M gamma gamma, and you kind of see a blip like this. At as Csaba mentioned earlier, the mass is 125 GeV. So you may have by now something like 1,000, 2,000 of these events. sitting on top of a quite a bit larger background. But you can still see a bump because QCD doesn't usually make bumps. This is all a smooth background. And another primary mode is this one, ZZ star. And so that one is a bit smaller. In fact, coincidentally, I just saw today, well, it came out a little while ago. You might, if you're interested in this, you can go check out this paper here, which is Atlas's update of ZZ star, where they had an integrated luminosity from the last run, but not quite all of it, 36 inverse femtobarns. And so they found in the ZZ star decay, they found 100 events, roughly. These are very clean. So this has very little background, this particular mode. This has a lot of background, but you can subtract it easily by extrapolating underneath the bump. So this has very little background. So with 100 events, what kind of statistical uncertainty can you get on the measurement of the Higgs production and decay in this mode? So what's the Poisson uncertainty on 100 events? Plus or minus goes like the square root of 100, right? So this 100 is plus or minus 10. So that means that the uncertainty in the cross-section that they measure, statistical, is about 10%. They have other sources of uncertainty too. But this, what they're really measuring now is a probability of, first of all, producing the Higgs, and the dominant way of producing it is from two gluons inside the proton fusing by making virtual top pairs that then radiate the Higgs, because the Higgs has a large Yukawa coupling to the top, and then this Higgs decays into ZZ star, which goes to leptons. So what they're actually measuring is the cross-section to produce the Higgs times the branching ratio for Higgs to ZZ star. And so, roughly speaking, this is measuring the Higgs to TT bar coupling through this virtual loop. And then you're also measuring the ZZ star coupling. And both of these are squared because they appear in the amplitude. So you're getting this product then. If you take the square root, the uncertainty goes down by a factor of 2. So you're getting some product to the order of 5%. So it's very statistically limited, and that's one of the reasons for running the LHC a lot longer than it's run already, to try to bring down these uncertainties in order to try to test the nature of the Higgs boson at the few percent level. This is sort of the best case. Other couplings are much harder to see, and they're currently at the 40% level or something, like B's and taus. They're much harder to see the Higgs, but there's evidence for them already. Okay, now I want to just spend a little bit of time on what's called the QCD improved Parton model. I'm not going to go into a huge amount of detail, but I just wanted to indicate roughly how are these calculations done and what is the role of amplitudes in the calculations. But we're not going to do any real QCD calculations with all the numbers in them. So for a general cross-section, and here I'll just consider that Z1 as an example, we usually calculate inclusive cross-sections. So we ask for a particular particle in the final state, but we don't put restrictions on other things that might enter. For example, jets that recoil against the Z. We can also ask for them too, but this is called inclusive Z production. So let's draw that picture again. We have two protons coming in. In lowest order QCD, the Z is always produced by what's called the Drell Yin process, where a quark annihilates with an antiquark to make a boson, and then you get decays into these leptons. But at higher orders, it will also be possible for a gluon to come in, and the gluon can fluctuate into a quark and an antiquark, and one of those can annihilate with a quark from the other side. So in general, we have to sum over these the partons inside the proton, and these quantities here are called the Parton distribution functions. Or just PDFs for short. And they give roughly the probability as a function. So if this has momentum P1 and this has momentum P2, then this probability depends on the fraction momentum. So this will be x1 times P1, this momentum here. In this approximation, this quark is collinear with the proton, and this antiquark is collinear with this proton and has momentum fraction x2 of that momentum P2. And then this is called the hard cross-section sometimes, or the short distance cross-section. And then there are some scales here that this is the renormalization scale. So you have to, this dependence often comes through the strong coupling runs with scale, and so you need to specify what scale you're going to evaluate it at. But there's also some explicit dependence beyond leading order on this scale. So mu r, the renormalization scale. And it's an arbitrary parameter, and if you had calculated to all orders, the answer would be independent of it. So you often vary to estimate uncertainties due to truncating the series when you only have calculated to a few orders. And then there's another scale here, which is called the factorization scale. So this picture where we factorize the process into pieces which describe the structure of the proton times a short distance collision, that depends on where we draw this box. And what happens is that at higher orders, before the partons annihilate into the Z, they could radiate gluons. Roughly speaking, if the gluon radiation happens inside this box, then we consider it as part of this short distance cross-section. But if the gluon radiation appears outside the box, we think of it as part of the proton structure. And as you change the size of this box, so this size, spatial size, is really like 1 over, because mu f is a momentum scale, and it's related to the size through the uncertainty principle, 1 over mu f. So as we change mu f, the size of this box changes, and we move pieces from the proton structure into the short distance cross-section and back again. And there are evolution equations that say that if we had calculated these things to all orders, things should be independent of the factorization scale. But in any actual perturbative computation, there are uncertainties that can be assessed by varying the scale and seeing how much the answer changes. And then we have to, these can be taken from, these are non-perturbative quantities, and they're taken by from fits to experimental data. Including things like the measurements at Hera of structure functions and deep inelastic scattering, but also the Z production data now at the LHC is coming into those fits, W and Z production. Okay, any questions about that? General setup? So now we have to, so we take these PDFs from various global fits. For example, NNPDF, MRST, which is now MMHT, CTEC. There are different groups that provide these functions. And then you go off and calculate the short distance cross-section for whichever process you want. And at leading order, we calculate the cross-section, roughly speaking, as sigma hat is just as an illustration. In this case, it would be for A plus B goes to Z, where A and B are Q and Q bar, where you have to sum over which proton contained a quark and which one the antiquark. And then you take this matrix element, a complex number, and you square it, and then this bar means it's usual that you take the answer, you sum over the initial and final spins and initial and final color configurations, and for m squared. And then you have to divide by the number of initial spin states and the number of initial color states. And in this case, these factors would be for quarks just 2, 2, 3, 3, and so on. And that's how you get the cross-section out in general from the lowest order amplitudes or the Born graph. So just to so you're computing something like this. Maybe you'll include the decay to leptons and all the angular correlations. So now we want to ask, what does the picture look like at next to leading order? So there are going to be two kinds of contributions at next deleting order, and each one of them is going to be divergent and need to be regulated. There are going to be virtual corrections and real corrections, and they will have infrared divergences that only cancel after doing a particular integral over the phase space for the real corrections. So here we write M as M0. For a general process, this might include some powers of the strong coupling. In this particular case, there are no powers of the strong coupling. They're only electroweak. But then in the NLO QCD result, every time we have a quark gluon vertex, we get a factor of the strong coupling GS, or if we have, which isn't going to happen in this process, but if we have 3 gluon contributions, we'll also get a factor of GS. And then the correction to the full amplitude can be written as M0 corresponding to tree level, M1 corresponding to one loop diagrams, two loop, etc. And then we need to square this cross section, and so then we'll get this Born term, and alpha s is gs squared over 4 pi. So then this will give us a factor of alpha s over 2 pi times the real part of M0 dagger with M1. So this is the virtual correction to the cross section. Maybe I should. And then the real emission divides up into two cases. We can, now let me just draw this. This is a typical virtual graph with a gluon exchange between the quark and the antiquark, and then this indicates that we've interfered it with the lowest order graph for QQ bar. So that's a sketch of the virtual correction, but then we can have real emission, which will include gluon emission, so before the quark and antiquark annihilate, so here's a Z. You can emit a gluon, and then you should square this graph to get a corresponding contribution to the cross section. And then the second thing that can happen is that you can have a gluon incoming and emit a quark. So something like gluon here, Z here. So this is the process. QG goes to ZQ. Actually, I forgot to, I meant to show you earlier a little sketch of what the Parton distributions look like. So So let me just do that now. Sorry about that. So the Parton distributions, as we were saying, depend on the value of the factorization scale at which you evaluate them. That depend on the resolution that you're looking at the proton. But when we're producing things like the Higgs and the Z, the natural scale is about 100 GeV. And then you can plot them versus X, sometimes called Bjorkane X. And here's a little plot on a log plot. This is actually X times f of X, which is the right thing to plot when you're on a log plot. Anyway, there's a so this is U valence, which is U minus U bar. And this is D valence, which is D minus D bar. And then the gluon is actually so large that you typically plot it divided by 10. And then you have antiquarks, D bar and U bar, coming in. And charm and bottom come in like this. So they're all very steeply falling or very steeply rising as you go to smaller values of X. So so this is this characteristic distribution, and this is called the valence bump. So it reflects the fact that proton at the valence level is 2 up quarks and a down. But of course, when it's boosted relativistically and looked at short distances, those quarks can radiate gluons, and the gluons can be considered as part of the structure of the proton. And furthermore, those gluons can also split into things like charm quarks, and at large scales, the charm quark should be thought of as part of the proton too. So an exercise related to this, and this back of the envelope type of stuff we were talking about earlier, is to design a PP bar collider to discover the W's and Z's. Now, you don't have to design the whole thing. All you have to do is estimate the energy, the center of mass energy. So all I really mean is what is the root S? Okay? So the idea is that if you have a PP bar collider, you can use this valence bump twice, because the distribution of the up quark in the proton has a peak, because that's part of the valence structure of the proton. And the antiproton, by charge conjugation, has a valence bump in the U bar distribution, which is exactly the same as what we usually call U in the proton. Okay? And similarly for D. So what you want to do is to make sure that your collider can produce the W and Z in a region around here, between about 0.1 and 0.2. That's where the that's where you get to see you get a little bump, and that allows you to maximize the cross section. So try to figure out the kinematics. Remember in that formula, remember the formula for, or rather you should work out the following formula as part of that. So this is called the Parton center of mass energy as a function of x1 and x2 of the two partons. And you can use that to help you design your collider. And then check to see if you got the right answer. And the answer is the SPP bar S collider at CERN. Okay, so that was a little aside to the structure of the Parton distributions. Now we should go back and take another look at these contributions. And I said that both of them diverge. So let's talk first about the virtual divergences. So these divergences are all what's called, well, IR, by which I mean soft plus collinear. The soft emission of a vector particle, either a gluon or a photon, is quasi-classical. It's sort of long wavelength. It's independent of spin of the emitting particle and only cares about color. So, for example, if we look at a scalar which has color A and color B, and it emits a gluon, which has a polarization tense vector. Let's call it nu, and let's call this soft momentum K. So this one will be P minus K. This would be P going this way or minus P outgoing. If you look up the Feynman rules, and this can have a color index S, you look up the Feynman rules for this. This will have a color factor. If this is an adjoint particle with the adjoint label A and B, then this will be proportional to the generator matrix in the adjoint representation, which is also called the structure constants for the Lie algebra. And then the kinematic factor is the difference of these two momenta. So it's something like minus 2p plus k. And that is supposed to be evaluated for this polarization of the gluon index nu. And now in the soft emission, we'll have k much less than p. So basically it's just proportional to the momentum of the hard line of this scalar. So that's the case of emitting off a scalar. What about a fermion? If we draw the same diagram for a fermion, where we have A, B, nu s. Well, if there was an adjoint fermion, for example, a gluino, it would be the same structure constant factor. And then, well, normally we omitted a factor of, there's a 1 over p squared for this propagator. This is a 1 over p slash for a fermion. And that's p slash over p squared. So let's put that p slash in there. And then let's put in the standard gamma matrix for coupling a gauge field to a fermion line. And then we get to put in the fermion polarization, which is spinor u evaluated at p minus k, which is roughly equal to p. But now we can do the following. We can commute this gamma matrix across using the anti-commutator. When the p slash arrives on this side, the massless Dirac equation for this quark says it annihilates. So the only thing we get left is this 2 eta mu nu contracted with p. And so we see once again that we get a factor of FABS times 2p nu. So the same factor we got in the scalar case. Okay, so now I have another exercise. Do the same analysis for emitting off a gluon. So look up the 3 gluon vertex, and in this case, besides index nu, you'll have a mu1 and a mu2, for example, and show that you again get this kind of factor, along with something that eta, you're going to get a eta mu1 mu2 to propagate this index along. So that will verify this statement that the soft emission doesn't really care about the nature of the particle. It's just this one factor. So now we're going to use this result in this amplitude here. And we'll get, just looking at the kinematic part of this, we're supposed to take this momentum here and get a 2p. Suppose we now call this p1 and this p2. We're going to get up to overall factors, a p1 dot p2 coming out from contracting this p1 factor with this p2 factor. And then otherwise, all we get are scalar propagators. And let me give this momentum L. So then we'll get a d4 minus 2 epsilon L. This is now in dimensional regularization. And we always need to introduce a mu, or mu r. So that loop momentum is L, L plus P2, and L minus P1. There's also some, anyway, this is basically the form that you get. You get these 3 scalar propagators. And now you see that there are going to be divergences when L gets close to 0, because this propagator is going to vanish then. And also these quarks are massless, so in that limit, this propagator also vanishes because P1 squared goes to 0. And also P2 squared is equal to 0. So you get sort of 3 propagators vanishing at once when the loop momentum goes to 0. So that's the soft virtual divergence. But then there's also a collinear virtual divergence. Because L doesn't have to go to 0, it could also become parallel to P1. When, let me write parallel, proportional to P1. Because when L is proportional to P1, because P1 squared is 0, this propagator vanishes, and this one vanishes. In that case, this third one doesn't vanish. This becomes, this is still non-vanishing, but you get a singularity when these two go to 0 in the collinear limit. So you have soft divergences, collinear divergences. I mean, I actually cheated a little because you can't really do this analysis in the collinear region, but the answer is still more or less the same. You have these overlapping soft and collinear divergences. As a result, when you actually do this integral, you get this is S12 is defined to be P1 plus P2 squared, and because these are massless, that's the same as 2P1 dot P2, and you get some gamma function prefactor. And maybe some powers of 4 pi or something. Never mind that. But the main thing is you get a 1 over epsilon squared divergence, and then you get another factor of mu squared over S12 to some power from this integral, and the S12 is canceled. Well, let me actually put this in here. So this should be like something like that. So you get these double poles in the dimensional regularization parameter epsilon, the dimension of space-time, and these should be canceled by the real emission, which I've since erased. So just very quickly, the structure of the real emission So there was this one process where we emit an extra gluon. This gluon has a divergence when its emission is very soft, and another one when it's collinear. So this gluon, well, we'll see this in more detail later once we start looking at examples of amplitudes, but it's going to have the same kind of soft divergence for real emission that we saw on the virtual side over here. And also, when it becomes parallel to this quark, when this angle here becomes very small, there's going to be a logarithmic integral divergence d theta over theta. And that together, when you combine both of those, that's going to give a 1 over epsilon squared. And then the second process we talked about, QG goes to ZQ. In this case, there is no sort of singularity associated with soft quark emission. These classical things require you to have bosons to give a divergence, but you can still get the same kind of collinear. So this has only a collinear singularity. So there's just a single 1 over epsilon. So when you add these terms and these terms, the divergences don't quite cancel. There's still, so when we do virtual plus real, there's still a 1 over epsilon left over. And that divergence is associated purely with collinear singularities, and it's associated with the need to renormalize the Parton distributions. So the Parton distributions are about the structure of the proton, but they're really matrix elements of operators inside the proton. And those operators need to be renormalized too. And I think I'm pretty much at the end of my time. So we'll talk about that next time, unless there are any questions. Yep.